All right, hello and welcome to another episode or another continuation of a previous episode of How to Understand X. Today we're going to be talking about sequences again. This is going to be a relatively informal exploration of the different types of sequences and partial sums that we might be able to use. And it won't be super in depth. We'll just talk about operations you can do and some of the larger ideas within sequences and some important things that happen within them. So I am just going to go down this list of sequences that I have right here, and we are going to start off with a rather interesting one, the plus or minus 1 sequence. So this is like, again, sort of like negative 1 to the n. We can even write that this is a sub n is equal to negative 1 to the n. And again, like we said, for most of these, this is a sub n, with n being in n, right? You have a taking in n as input, and n is within the set of natural numbers. That's all that that's saying, so this is just sort of implied for all of the sequences that we're going to be looking at today. And for this one, you plug in 1, you will get negative 1, right? You plug in 2, you'll get positive 1. 3, you'll get negative 1, 1, negative 1, and then on and on. And this might be relatively boring because what's even really happening with this? And if you just sort of graph this, like if this is 1, 2, 3, 4, I'll just, you know how to count. We go negative 1, 1, negative 1, 1, negative 1, 1, negative 1, right? And this is called oscillating, or oscillation. I would just say that the sequence oscillates. I don't know the actual noun form of it. But this sequence oscillates because you're going between two values, but you're not converging to either of those values. And this, again, is more important within the context of series. If you have an alternating part or a sine sequence that is multiplied to an actual sequence, then you will get more interesting series, and a series that may or may not converge conditionally if there is an alternating part. But, not too much to talk about here, but there is a very nice idea within discrepancy theory, that being like discrepancy theory is almost exactly what it sounds like. It's how often or what qualities or situations arise in discrepancies from the expected value or norm. So Wikipedia just says it's the deviation of a situation from the state one would like to be in, which is unnecessarily complicated. It's just this, it's like the reason why things are not what they're expected to be, right? It's like error bounds, and discrepancy theory is really cool, but it's not really useful if you're not studying math fully and not just learning it for us. But Paul Erdos, a very famous mathematician, I would say probably one of the most famous mathematicians of all time, he came up with this very nice uh, problem that follows like this. The absolute value of the series from n equals 1 to k of sequence x sub I times d, so this is still part of the inputs, is greater than c. And this x sub I times d is the sequence that we're working with, a sine sequence, right? And it's saying that this sum, if there's an absolute value being taken, right, this should be greater than c. But this is a discrepancy with the idea of oscillation. Um, like it's sort of poking at the idea of when we take absolute value, right? Because absolute value, if the absolute value of this was taken, then this series would obviously diverge, right? If you're taking the absolute value of this, you will always just get 1 to the n, which means you're getting 1, which means you're just adding up 1 a countably infinite number of times and getting infinity. But if you're taking the absolute value after this sum, you can sort of write it out as -1 plus 1, -1 plus 1, -1. But this is all within an absolute value sign. And this theoretically should be greater than c, right? Because you don't know where you're stopping. If you stop at a -1, you will get to a absolute value of -1, which will get you 1, right? And if you have a 1, then you will get the absolute value, which is 1. And more of a thought experiment than actually something that we're going to work, because, again, this is a discrepancy problem, which means that it's not really solvable. There are some proofs out there, like some crazy stuff's going on, but it's just like a fun little thing to think about. And again, not super important for us, but it's just, if you want to remember something, just remember that -1 to the n makes other sequences conditionally convergent if it does not converge already. And there's also an arithmetic sequence. I would say that this is actually rather similar to a geometric sequence, but it's say, how should I explain this? So, an arithmetic sequence is just a sequence where there is a common difference, right? And this difference is constant. So if we say that a sub n is our sequence, we start at a sub 1 plus n minus 1 times d. We start at n minus 1 because, well, we already started at 1. We have a first term, right? And, well, it doesn't necessarily need to be 1. If this was a sub n is equal to a sub m plus n minus m times d, this is also, perfectly reasonable. And this is just saying a sub 1 is the first term, d is the difference between consecutive terms, and this difference is constant. So, for example, if you have 1, 3, 5, 7, 9, and on like that, as you can see, there is a difference between each term, and that difference is constant. That difference is 2, right? And a sub 1 is going to be 1 in this situation, and n minus 1 will be multiplied by each of these values, right? You're going to have 2 times 1, essentially. 2 times 1 plus 1, which will get 3, and then what would it be? It would be 2 times 2 plus 1, which would get you 5, and then 2 times 3 plus 1, which would get you 7, and on and on. But you do have a starting term, a first term, and a common difference. This is similar to a geometric sequence, but the difference between geometric sequences and arithmetic sequences, we can even write out what a geometric, so let's write this out. This is arithmetic, right? And then this is geometric. This geometric sequence looks like this. You have a times, a plus a r plus a r squared plus a, I'll put the ellipses to sort of say that this is continuing, plus a, okay, plus dot 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 plus a times r to the n, right? The nth term, this is geometric. And this is similar to this, right? You have a first term, a, or a1, and you have a common thing that is happening to every subsequent term. This is an addition, and this is a multiplication. This is a difference, and this is a ratio. So, just a good idea to remember. And the sum of, well, this is obviously going to diverge, right? Like if you have natural numbers, this will diverge because you are increasing. If it is, odd numbers or even numbers or most arithmetic sequences, they will diverge if you're doing the infinite series for them. But if you do a partial sum, which is what we will most likely do. The arithmetic series is what we call these partial sums. We'll get to geometric series in just a second, so don't worry. But if we do the partial sums of arithmetic series, we have n times a sub 1 plus a sub n to 2. So this is the partial sum from, well, you don't know what n is equal to. So I'll just sort of write out, we're going to n, right? Yeah. How should we start this? How should we write this? That's a better term. Let's just say that this is the sum of, let's just write this how we did other partial sums. We'll say that this is the partial sum up to n number of terms of, an arithmetic series. So let's try and prove this, because I think it is quite the interesting idea. So if S sub n is the sequence that we are trying to do, the partial sum sequence, right? We have S sub n is equal to a1 plus a1 plus d, right? Plus a1 plus 2d plus a1 plus 3d, and on and on. Again, if you just sort of think about this, the common difference is the same because it's common, and n minus 1 will not be included for this first term, but for every subsequent term, so for example, n equals 2, n equals 3, n equals 4, you do 4 minus 1, you'll get 3, 3 minus 1, you'll get 2, 2 minus 1, you'll get 1, and this is how this arithmetic series will look, right? And you add up to, say, a1 plus, n minus 1 times d, even though I would say that's relatively obvious because you're summing up to n, right? So you're going to have to stop at the term that comes before it, which is n minus 1, and, not stopping before it, but you're going to stop at that term, right? And this is, again, just another way of writing what we originally had, a sub n minus n minus 1 times d. So S sub n is equal to a sub n minus 1 times d plus a sub n minus n minus 2 times d, and then, on and on in this sort of manner until you get to, a sub n, right? You're going to go to a n minus 2d, and then a sub n minus d, and then plus a sub n, right? And, yeah, I would say that makes a good deal of sense. And now we can just sort of say that if we add these two together, right, if we add both of these equations together, we are going to cancel out every one of these values except for a sub 1 and a sub n, right? We're going to have 2s sub n is equal to n times a1 plus a n, right? Because, let's try and think about this. If you add these, right, this becomes negative n plus d, right? And, you're adding plus 2d and plus 3d. So these are going to be similar, but you're starting with the minus n minus 1, right? So if you factored out all of those values, like nd, it's going to be negative nd plus d, negative n plus 2d, and on until you get to a sub n minus 2d, and then plus a sub n minus d, right? You're just doing negative n plus d, negative n plus 2d, and eventually you will just get to minus 2d, minus d, and eventually nothing. So all of these cancel. You have 2d minus 2d minus d, and once you get to the end values, so once you get to a sub 1 plus n minus 1 d, right, this will cancel out with this. And the only things that are left are a sub 1 and a sub n. So it's like these are essentially just writing the same thing in two separate ways, but just like flipping the order so that it's sort of like a telescoping series, and that you just flip the order, and then the last few terms cancel out the first few terms, and then vice versa. So we're left with only n times a sub 1 plus a sub n, and then, we just divide both sides by 2, and we say that s sub n is equal to a, well, n times a sub 1 plus a sub n over 2, right? And yeah, pretty okay, I would say. And this is a little bit more tricky to really do. I don't think we have, any specific need to do this, but we might. Depends on what you're doing within sequences and their respective fields, because we don't only do calculus on this channel. We do other stuff, set theory. I think that's the only example of me doing something other than calculus on this channel. But we do stuff, theoretically, other than calculus. So we can go a little bit further into this idea. We can say that a sub n, if we were to find the product of the members of a arithmetic series, right? Because arithmetic series have to be finite, because if it wasn't, it would just diverge to infinity. If we were to find the product of every single term, so a sub 1 times a sub 1 plus d times a1 plus 2d up to a1 plus n minus 1 d times, well, this is actually the last one because, you multiply it up to this value. We can call this a gamma function and, do the correct notation for this. So it looks like this. Again, we're not going to spend too much time on this. We're just going to sort of show it and then move on. But we have a1 plus kd, right? Because this is being increased by a factor of k. And the product of this progression is going to be a factorial, right? So let's see what the... I'm not going to do a full proof of this, I don't think. I don't think I would know how to do a proof of this. But the idea is that you are, summing up some values. Like you're just doing an operation. This is a gamma function, so it's the product of everything. And k is the factor by which d is being multiplied. So this is sort of like a factorial, right? You're doing, if you just thought about this in the opposite order, like 3d times 2d times d, you are, doing a factorial. And yeah, this is an operation that you can do, and this is equal to, well, this isn't the product itself. This is just this is product instead of series, but if we do d to the n times gamma of a1 over d plus n over gamma a1 over d, that's what this is equal to. Again, I barely know what this means. It's more just like you can do further operations with arithmetic sequences than just the sum, but for our purposes, I would say that the sum is more important than the product. So that was arithmetic sequences. Now we can go into, let's go into geometric sequences. Again, we talked about this in the previous video, but you start off with a as the first term, and then ar squared, ar cubed, and then on and on until you get to ar to the n. This is a sub n, and this is a geometric series, right? And again, you can do the same type of product. This is the product starting from I equals 0 up to n of a r to the I. So, it's going to be a r to the 0 times a r to the 1 times a r to the 2 times a r to the 3 is equal to the square root of a squared times r to the n plus 1th power. But, not really necessary for us. We did talk about how this series has a sum, but again, just to review, a is the first term, r is the ratio. If r is less than 1, then we have a convergent series because each value is a fraction of the value that came before, so it's therefore much smaller than the value that came before. And again, we can generalize these. I think I already did this proof, but very quickly, we can just say that if you have a series, well, this is actually a new proof, a new way of writing this proof, so that's cool. Let's do that, actually. So, just now looking at this proof, we have k equals 1 up to n, right? Normal stuff, a r to the k minus 1, so that we start at a times r to the 0, so we start at a, and this is going to be a plus ar squared, so this is the series that we're working with, right? And if we multiply everything by 1 minus r, we're going to have 1 minus r times ar to the 0 plus ar to the 1 plus ar squared. I know I'm not writing these very well. Ar cubed, and then on and on. And this is going to be equal to ar to the 0 plus ar to the 1 plus ar squared, and then on until you get to minus ar to the n minus 1 minus ar to the 1 minus, ar squared, and on until you get to minus ar to the n. So again, you are multiplying 1 to this infinite series still, so you're going to have the same infinite series for this part, but you're also subtracting, well, r times this product. So that's where this negative comes from. You're doing minus ar to the n minus 1 and on and on. But as you can see, these terms are sort of like telescoping series. You are adding and subtracting, so these terms will eventually cancel out, and this will also cancel out. So you're only going to be left with a, which is a times r to the 0, this term, a minus a times r to the n, the last term in the series. And yeah, so that's pretty cool, I would say. So now we have 1 minus r. I'm just going to say that this is the sum up to n, because that's what it is, right? The sum up to n is equal to a minus a. Well, let's factor out this a just to make this nice and general. A times 1 minus r to the n over 1 minus r. That's what this is, right? And if this series converges, which it can, if this series converges, That means that r is less than 1, which means that we have a fraction, which means that r to the n is approaching 0 as n approaches infinity, which means that you will generalize to a over 1 minus r if and only if the series, the infinite series, converges. But if it doesn't, then this is a perfectly fine way of doing the partial sum a times 1 minus r to the n over 1 minus r. And that's, perfectly great. And if k is not explicitly equal to m, the value is still relatively similar. Like, for example, if we started at m, and this was m plus 1 and m plus 2, we would just, m plus 2, m plus 1, we would eventually still cancel out these ones. And so we'd still have a similar proof at the end of it. We're still going to have a times r to the m minus ar to the n plus 1. And so when we plug all this in, I'm going to erase this because this is getting egregiously messy. Once we divide both sides by that 1 minus r, we are still going to have a nice sum of, from k is equal to m up to n, we're going to have a nice sum of, I'll just say a sub n, a times r to the m minus r to the n plus 1 all over 1 minus r. And I'm not sure if I'll do like a video practicing these partial sums. I think it's probably better to just sort of know them, because at least for my channel, which focuses mostly on calculus, I know I'm just contradicting myself after boasting about how much I don't focus on calculus, but since we focus mostly on calculus, this isn't strictly necessary. I feel like I'm going to regret saying that, but this isn't super important to us, but the ideas here are very cool and very interesting. And again, if r is less than 1 and this series converges, then this is approaching 1 and this is approaching 0, which means that a times 1 minus 0 will get you a over 1 minus r, which is again the sum of the infinite series that we have talked about. So yeah, that was a nice review of what we were talking about beforehand. Now let's get into some new ideas. I hesitate to say new because I feel like I've already mentioned some of this, but again, harmonic series. I'm just going to go through that once more. Harmonic series starts at n equals 1, and it looks like, or harmonic sequence, 1 over 1, 1 over 2, 1 over 3. This diverges, the series diverges, even though the value, the test for divergence, like the nth term test for divergence, is inconclusive because 1 over n does approach 0. By the integral test, you can prove that this is that this is that this is divergent, and you can also use the integral test to talk about p-series, which again is similar to harmonic series, but you just do use different degrees. And p-series, I don't think I need to explain any further. I'll just sort of go over it once more. 1 over n to the p for increasing values of n within natural numbers. You go 1 over 1 to the p plus, or 2, 1 over 2 to the p, and then on and on until you get back to 1 over n to the p. And these, like, these converge, this series. If you add up every term, this will converge if and only if p is greater than 1. If p is equal to 1, we get a harmonic series which diverges, and if you get something less than 1, it will diverge as well. And so now we've gone through some of the ideas that we talked about beforehand, and now I actually want to talk about something new, which is exciting because, how much more is there to talk about sequences, right? But we have something pretty cool. We have the Cauchy sequence. And the Cauchy sequence is sort of like the alternating series, like what we've been talking about. It's essentially saying that you are bounding a series. That's the point of a Cauchy sequence, that you are giving a sequence bounds. And the formal definition of a Cauchy sequence is if you have a sequence like x1, x2, x3, on and on, and these are real values, this is a Cauchy sequence if for every positive real number epsilon. So epsilon is a real number, right? And it is greater than 0, which does not narrow it down, as we talked about in the set theory video, and I feel like in a couple other videos, like in our definition of sequences and how they're different from functions. We did talk about how, real values, the set of real numbers is uncountably infinite. So for every positive real number, that is not narrowing it down at all. Like, you know how the series, or the, what? No, the set 1 to infinity with n in n, this is countably infinite, right? This is aleph null, and the series, or the, I don't know what is happening, the interval 0 to 1 with n in real numbers, so the number of real numbers in between 0 and 1, is uncountably infinite. So this infinity is quote-unquote larger than the infinity of every countable natural number. So that's pretty crazy. This isn't, all of this is to say, this isn't really saying too much, right? And we, like for most of these types of things, we're going to say mn is greater than n, some arbitrary positive integer, so natural number, and we will say that x m minus x sub n is less than epsilon. Again, this is like tolerance. You have negative epsilon is less than x sub m minus x sub n is less than positive epsilon. So this is sort of like the bounds. The idea behind the Cauchy sequence is that you have bounds, and this distance between the subsequent terms is supposed to be infinitesimally small, as epsilon is, of course, a very small value, right? And that's sort of how it looks like. Let's try and draw what this would even be like. So it's sort of like, if this is the asymptote, if you thought of this as an asymptote, then you are going closer and closer to a specific value, right? If this is negative epsilon, I'll just draw negative epsilon as a bound. Oh, this is positive epsilon. I'll draw this negative epsilon, this is positive epsilon. If epsilon itself, this epsilon, is approaching 0, then this bound between negative epsilon and epsilon is decreasing. That means that it's sort of like a string, you're getting closer and closer to like this one value. It's like a, this is really dark, it's like a dying heartbeat. I'm sorry. So, okay, we'll ignore that thought. But, you are going, it's sort of like oscillating, you are going closer and closer to some predetermined value, and x. So let's try and draw this slightly better. If we have this is zoomed in, if this is x m, right, x sub m, and this is x sub n, then the distance here, if this is still a Cauchy sequence, which means it's like, being bounded, then the distance here is decreasing as epsilon itself, like this value and this value, is decreasing. So the distance between x sub m and x sub n, or x sub m minus x sub n, is going to be less than epsilon, which is approaching 0, right? It is a tolerance that is becoming smaller and smaller. So that's what a Cauchy sequence sort of is. I know I'm making it sound a lot more complicated than it actually is. It's just a sequence that is being bounded, by a upper and lower limit or value. And as this value decreases, then the tolerance that is given also decreases, and you are converging to a single value, and the sequence has a limit. But you are both increasing and decreasing. It is not monotonically increasing or monotonically decreasing, because you're going increasing, decreasing, increasing, decreasing for every other value. So it's like an alternating series, but it is converging to a specific value. And yeah, that is a very brief, probably insufficient explanation of Kashi sequences, but for our purposes, I did talk about Kashi sequences in the series video. Spoiler alert, already filmed it, but yeah, Kashi sequences are just sequences that are bounded by some tolerance that is decreasing, and since epsilon is only defined as a real value that is greater than 0, that can be literally like 0.000 on for like 2 trillion zeros and then 1 at the end. So it can be a very small value. And as epsilon is decreasing, the amount of tolerance that is afforded to x sub m minus x sub n is also decreasing. So yeah, that is a Cauchy sequence, just a sequence that is being bounded by epsilon. At least that's the way I sort of think of it. It's not probably the best way of like understanding it, but it is, it's acceptable for our collective knowledge. And let's talk about another thing. This is the Cauchy product. I'm not going to, do a proof of this, because this is a pretty crazy idea, especially because, it's not really necessary for us, I wouldn't say. But the Cauchy product works if these infinite series have complex terms. So if you have a series from I equals 0 to infinity of a sub I times the series from j equals 0. I know this is looking like vectors, but from j equals 0 to infinity of b sub j, you are going to have the series from k equals 0 to infinity of c sub k, where c sub k is the sequence of, well, the sequence of partial sums up to k of L. Let's try and draw it like L is equal to 0, where you have a sub L times B sub K minus L. So that's pretty crazy, like in terms of what's even truly happening. But the idea is essentially you can do the product of two series with complex terms if the resulting series that you've created from this product is just the sum of opposite terms. So if you have, say, L is equal to 1 and K is the maximum number of terms, so it's like the first term times the last term, the second term times the second last term, third term times the, let me draw it. You have 0, and let's say K is 6 or something, right? 0, 6, 1, 5, 2, 4, 3, and then 3, and you would just sort of do it like that. You're multiplying the term by the term that is farthest away from it, and you're not repeating. That's what's happening with this Cauchy product, and it's sort of like in stats. I don't remember exactly what the application of this type of sequence is, but I have seen this sort of notation for like things in stats where you multiply the first thing by the last thing, and then you add it, and you continue doing that. So this is a Cauchy product of two infinite series, which makes it simultaneously crazy to think of, but also very cool. It's hard to like explain it though, and I don't think I did it justice, and I probably will not do it justice. I've been trying to find a proof that I can understand and like explain at a reasonable like level, but I have yet to do that. And we can also this also applies for power series, even though we have not gotten into power series, and we most likely will have to get into power series at a later time. And you know, what else? What else? We have the Fibonacci sequence, though it might not have too many applications outside of, just being cool. It is cool, right? You start at 0, 1, and then you just add up every term. And this is a perfect introduction into recursion. We're not going to get too into recursion because recursion is, again, not really a calculus concept. It's more of a computer science idea, set theory idea. Well, what am I doing? This is 5. I used to know the Fibonacci like the back of my hand. 5, 8, 13, 21, 34, and on and on. But, you just go on like that. This is a recursive sequence because every subsequent output is affected by the previous outputs. So let's talk about what a recursive sequence is. Again, recursion appears most commonly in computer science. Like for certain like coding principles, recursion is like a really important idea so that you don't have to reuse code, which is again another example of how math is useful outside of just this. But yeah, this is going into discrete mathematics, which I mean, we have been working almost exclusively in continuous mathematics because I mean that's what calculus is, the study of continuous change. But yeah, this is computer science and cool stuff that's going on, So the idea of a recursive sequence is you have, well, let's say a, well, order. Let's talk about order. Order is just the number of terms. So if you have this S sub n, this sequence, where you have C1 times S sub n minus 1 plus C2 times S sub n minus 2 plus, on and on until you get to CD, or not C times D, C sub D, C sub D, S sub n minus D. As you can see, you are summing up with the sums, or well, if this is a series, I don't know what I'm talking about. This is a series, and you were summing up the previous terms, and you're using the previous sums as inputs for this new partial sum. That's the idea behind recursive series and recursive sequences. You are just using previous outputs as inputs, and yeah, we're just sort of just look at it, like it's something to sort of think of. It is, useful, and like for like recursive sequences, you can actually write down the general recursive term as, inputs of other things. So for example, you can say that S sub n is equal to 2 to the n, right? This is a perfectly valid sequence where every single term starting at n equals 0 is the previous, well, not the previous, it is 2 to the power of that term's value. But if you were to write this as a recursive sequence, again, the C in this case is going to be 2, and the S sub n minus 1 is the previous inputs. For example, let's plug in S is equal to 1, right? S is equal to 1, you're going to get 1. Like, we'll start at the first possible value. S sub 0 is, well, it's not 0, but the first value, since we're starting within the natural numbers, the first one's going to be 1, and then you multiply the previous term. So if this is S sub 2, you do S sub 1 times 2. So S sub 1 was 1, so you do that times 2, right? And then you do the third term, so s sub 3 minus 1, which is s sub 2, so 2 times 2 becomes 4. And then s sub 4 is 4 minus 1, so s sub 3, which is 4, times 2, which is 8. And then 16. So you're still getting the powers of 2, but you're just writing it as 2 times the previous inputs. And of course, that makes sense if you think about it. 1 times 2, 2 times 2, 4 times 2, 8 times 2. This is a recursive sequence as well as a perfectly valid power, 2 to the power of n. And again, you know, you can also write alternating series like the plus or minus 1 sequence that we were talking about at the beginning. Instead of writing as negative 1 to the n, you could also write it as negative s sub n minus 1, right? Because you're multiplying a negative to every previous value because every value is 1. So you have 1 times negative previous value, so negative 1 times negative, so the third term is negative of the previous value, so positive 1, and then negative of the third value will be negative 1, positive 1, and then you go on and on, but the idea is still the same. You are having this very nice recursive sequence that is defined based on the previous terms. And yeah, that's very interesting in my opinion. You can also do decimal expansions with these values, which I think is fascinating. You know how decimals are actually sequences if you really think about it. Like for example, let's just let's think about what's a good example. So if you write trying to think of a good like one thing to show, but I'll just say it. If you think of a series as say 3 over 10 to the n, right? And this is a p series, or what am I? Oh, this is a geometric series. I am on something. You have 3 times 1 over 10 to the n, which is again 3 times 1 over 10 in parentheses to the n, which is a is equal to 3, r is equal to 1/10. But if you plug in 1, so let's plug in 1, you have 0.3, right? Because 3 over 10 to the 1 is 0.3. And 10 to the 2, or 3 over 100, is 0.03. And then 0.003, and then 0.0003, and on and on. But as you can see, you add this to that 0, this 3 to these 2 zeros, and then this to those 3 zeros, and you might be able to see that this is actually 0.3 recurring. Recursive recurring? No. But you can write these decimal expansions as recursive sequences, which I think is really cool. If you just define every subsequent term as the previous term times 1 over 10, then this is, of course, a recursive sequence, right? And yeah, so if you can just sort of wrap your head around that, I'm not like trying to make this particularly formal. I'm just sort of saying you can write decimals, all decimals, as recursive sequences. These are called decimal expansions, in which every other term uses the previous term as output. Uses the previous term as input for a new output to create an infinitely expanding decimal, which is all decimals, right? Like even ones that technically quote unquote converge. If you have, say, 0.1, you might be like, oh, that's 0.1, but it's also 0.10 and 0.100 and 0.1000. So you can write any decimal as an expansion, and you can use recursive sequences for writing these expansions. And I think that's going to be it in terms of just like this little addendum. This is a very informal video. I didn't really talk about anything. I think this is probably in the same range as like mathematical beauty, sort of just saying things that are cool. And so in that spirit, I'm not gonna pick a full album. I'm going to just look at my like playlist so far. I'm really, really tempted to recommend some more Nujabes, but I I can't. I can't just keep recommending Nujabes. That's my go-to at this point. Just telling people, hey, listen to Nujabes. It's like it's not. It's making me seem obnoxious, which I mean I am, but it's like it's not good for me. Um, let's see. Oh, there is this really crazy track that I heard a little while ago. It's a gangster rap. I think like the actual song is called Gangster Rap. Let me just check who's it by. I know Madlib's on there. I think Fatlip's on there too, which is a crazy deep cut. Like if you if you have heard The Far Side, not only can we be friends, please, but my God, like the fact that Madlib got Fatlip to do something in 20 in the 2020s, that's like insane. What's it called? I think it is just called gangster rap. Let me sorry, let me try and find it. Gangsta rap blue because blue is on there. Yep, yep. It's called gangster rap, and let's write this down. Gangsta rap by Fat Lip from the Far Side. You know, the '90s rap band that made "Passing Me By," Far Side 2. It's like they've made some classics. Lab in California. I mean, I wouldn't say they have like a super prolific discography because they didn't make enough to have a prolific discography, but both of their, you know, debut and sophomore albums, I think Far Side 2 is their debut album, but I mean, it is evidently a sequel because it's Far Side 2. But, Far Side 2 and Lab in California are really great records, even though, Far Side 2 is probably slightly, like, Bizarre Ride to the Far Side is probably slightly better. Not even slightly, it's significantly better than Lab in California, but, there's Running on a run in on Lab in California, but Passing Me By. What a fantastic song. But Fat Lip, I need to get on track. Fat Lip, Blue, and Madlib are all on this very weird, weird song. Like when I first heard it, I didn't like it because I thought it just sounded bad. Like it made my like brain sort of fuzzy because the vinyl crackle. Like, Madlib, I love Madlib, but it's a little bit excessive, honestly. The vinyl crackle was distracting, but you know, it's funny. Like the verses are funny, the chorus is funny, the instrumental is ridiculous. It's like it just seems like these people are having fun, and they just sound so young. Like they sound like teenagers, even though they're pushing like 40 and 50. It's like these are legends within the like alt sort of rap genre, and it's just the fact that these guys came up with this very very interesting record. It's so fun, like it's just fun to listen to. I really like it, even though it is garish. Garish is probably the. It's not a very nice word, but it's accurate. This is a pretty garish song, obnoxious, but in a good way. And yeah, if you like it, please comment down below. If you learned something from this video, please comment down below. If you did not like this video, constructive criticism is always encouraged. And if you're not in the mood for constructive criticism or a comment, um, I was actually gonna go work out after this, so that's why I've been sort of rushing this because I need to get down. But what am I gonna do? Do some. What are they called? Oh, shoot! It's like a like pylo, not pyro. It's like push-ups where you push up off of the ground. I know it sounds intimidating. I know it doesn't sound like possible if you don't have like if you're not The Rock, you might think, "Oh, I can't do that." But it's like you just practice. You do one of them every day, and then you do two of them every day, and then eventually, they just become your new favorite push-up because they're way more fun than normal push-ups. Normal push-ups are sort of torturous, and you activate more muscles. You get to air time. You get to be in the air slightly, and yeah, they're pretty fun. And you also can tap out after like 10 and be like, oh well, that was intense when 10 push-ups. But I mean, no hate towards people who are only doing 10 push-ups. Keep on keeping on. And I'm losing my train of thought. I need to stop talking. So yeah, listen to gangster rap, and bye.